This is AP Precalculus. We are on notes for part 1 on topic 2.13, exponential and logarithmic equations and inequalities. This is part 1 of part 2. There are 2 parts of the notes. It's already going to be a long video, as you can see in the time bar below. So I guess essentially we're putting everything we're doing in the past few lessons all into one lesson and making it into equation solving. So here is a review of all of our properties. There are a few of them that we've been using, and then this is the way that we're going to be solving for problems where we switch between exponential form and the logarithmic form. I have a slightly different way of solving these problems that I'll be talking about, but this is a completely valid way of doing one of those hard steps. So the first part of the notes is dedicated to equations that only have one log or one exponential function. So in general, these are the steps. You're going to isolate the exponential or the log expression on one side, and then you are going to write the equation to the alternate form. So you're going to switch between the exponential and logarithmic form. This is where Mr. Sindel does slightly 2 different things that I want to talk about now, and then I can review it later. What I do is I either take the log of both sides, or I'll do exponentiation. I thought that was the correct way of teaching it until I saw these notes, and I realized, oh, that is a completely valid way of solving the notes, and then you only have to learn one thing instead of 2 things. I'll be showing how to do it both ways, but I think long term, I'm probably going to go back to the way that I was taught. It makes more sense to me. Maybe this way makes more sense to you, though. And then you solve. And then you have to simplify or round your answer if you're told to do that, right? Most of the time it will say leave an exact form because you don't know how to, what is log of 3? I don't know, so you'll have to leave it in the exact form unless you have a calculator, right? I think all of the notes today do not have a calculator as far as I can remember. All right, let's jump in with some actual math now. We're going to solve the following equation. Here we go. So I need to isolate that exponential term, so I need to get rid of this minus 2 by adding 2 to both sides. I'm saying that out loud, I'm just going to do that. So I'm going to get 4 to the power of x is going to be equal to, if I add 2, I get 9. And then from here, we have 2 things that we could do. Let me go ahead and do it the way that Bryan Passwater is telling us to do it. He's telling us to write it in the alternate form. So this is what's called exponential form, and I want to write this in its alternate form, which is logarithmic form. So maybe I'll do this first path in blue. So if he writes it in in logarithmic form, you're going to say log base, whatever that base is, 4, and then you're going to switch these 2, right? The x and the 9 switch, so it's going to say of 9 is equal to x. We switch the x to 9 successfully, and then from here, we're done. So that's one way of doing it. And I'll get the same answer my way. So I'll do mine like lime green. The way that I was told to do it is if you're ever stuck with the x in the, I guess the exponent, I always think about this as Rapunzel being stuck in her tower and she needs to let down her hair or something. There needs to be some way of rescuing x. The way that you rescue x is you take the log of both sides. If you take the log of both sides, you get to choose what base you want to choose that log to, and I always choose the same base as our base. So what I do is I say, take the log of both sides, which means this 9 needs to move over a little bit, and I'm going to say, take the log of both sides. I'm going to choose this base for my logarithm, base 4, and then watch what happens. This is asking a question. What power does 4 need to be raised to get 4 to the power of x? Well, this 4 needs to be raised to the power of x in order to get 4 to the power of x, which is a very convoluted way of saying that stuff all cancels out and you are left with just x. So you can say x is equal to, okay, and then over here, what do you have? You have log base 4 of 9. So we'll say log base 4 of 9. So that's my way of remembering log base 4 of 4 to the power of x. These all cancel out, and you're taking the log of both sides. Whatever you do to one side, you do to the other side. It's preserving that balance of algebra. So I guess this way is simpler at first, but I feel like this is going to lead to more long-term success in these really hard problems that we'll be facing at the very end of this video. All right, part B. There's our exponential. We're going to save Rapunzel, who's trapped up in the tower right here. You're not part of the tower. I'm going to get rid of the plus 5 by subtracting 5 right now. If I subtract 5 on both sides, I'm left with 2 to the power of x plus 3, and that's going to be equal to, and then over here, I'm doing 26 minus 5, which is just 21. Okay, so now I have isolated my exponential. I don't have, if I had a number out here, I would divide by it, but I have no number out front. I need to save Rapunzel. So I'm going to take the log of both sides. I'll show you how fast I can go here. If I'm taking the log of both sides, I get to choose whatever base I want, and I choose the same base here. So log base 2, log base 2. And then we know that these cancel out, leaving x plus 3 is now equal to log base 2 of 21. And then from here, I just need to get rid of that 3, and I'm done. I'm going to subtract 3 on both sides. I'm going to say, might as well change the color, x is equal to log base 2 of 21, and then I just subtract 3 for my final answer. All right, let's try it again with part C. Maybe I'll try that change of form, a way of doing it, the Bryan Passwater way. So from here, I'm going to isolate this. Okay, be very careful. I don't want to isolate this piece. I want to isolate this piece. I can get rid of the 4 before I isolate the exponential. So I need to get rid of this 3, then I'll get rid of that negative 4. So first, let's move over to 3. I'm going to subtract 3 on both sides. That means I have a negative 10 because I subtracted 3, and the 3 is gone. So I now only have a negative 4e to the power of x. And now I'm going to get rid of that negative 4. I can get rid of it right now. I don't have to save Rapunzel yet. I'm going to divide by the negative 4. If I divide both of these by negative 4, what ends up happening is I have a negative 10 over a negative 4, which can be simplified. And then on the right side, I have just e to the power of x. Rapunzel is ready to be saved. Over here, I'm going to simplify this. I'm going to say this is really equal to negative divided by a negative is a positive. This is really just 5 over 2. So from here, I'm going to rewrite this in exponential, or this is exponential form. I'm going to rewrite this in logarithmic form. So I'm going to say, wherever the exponential function is, that's where the log goes. I'm going to say now log, and then this e is my base. So I'm going to say log base e, and then I switch my x and my 5 halves. So 5 halves comes over here, and you're going to say 5 halves. And then over here, you switch the x over there. So we say x is over here. And that's the final answer. But remember, log base e can be rewritten as just natural log. So you can say the answer here is natural log of 5 halves. I guess that is not that hard. All right. Let's move on to the second of 3 pages. The first part of the notes are 3 pages. The part 2 is 2 pages, but those 2 pages are rough. All right. We're getting slightly harder here. Again, we're going to solve for these and leave our answers in exact form. So again, I'm trying to isolate this logarithm. This logarithm right here, I need to get rid of a 2, get rid of a 4. I'm going to get rid of the 4 first. The reason that we get rid of addition and subtraction is we're undoing PEMDAS. I don't think I need to state this again, but I'll do it just for the video. So we have, please excuse my dear Aunt Sally. Whenever we simplify, if I don't have any algebra, then you go this direction to simplify. If I'm trying to undo things to x, I go this direction. So I always try to get rid of addition and subtraction. I try to get rid of the addition and subtraction first because you're undoing PEMDAS. So I'm going to subtract 4 on both sides, which means I'm left over with a 2 log base 3 of all of this x plus 3. And because I subtracted 4 on both sides, I have a 6. And then finally, I need to get rid of 2. The way that I undo this multiply by 2 is I divide both sides by 2. When I divide by 2, I'm left with log base 3 of this x plus 3. And then if I divide the right side by 2, I get 3. All right, so from here, let me try Bryan Passwater's way. I'm going to do a change of, I guess, what is it called? Change of form. So it's now going to be exponential form. So instead of saying log base 3, it still has a base of 3, right? So still base of 3. That's a bad 3. It's base of 3. And then I'm going to switch these 2 sides. So the 3 comes over here. So it's 3 to the power of 3. And then this x plus 3 comes over here, and I say this is equal to x plus 3. Okay, that actually works out pretty well if you like that form. And then from here, I can say, okay, 3 to the power of 3, who are you? That's 27. You should have those perfect cubes down by now. You can say this is 27 is equal to x plus 3. And then from here, you subtract 3 on both sides, and you say x here is equal to 24. Kind of a nice, simple answer. That was a weird rectangle. Come on now. There we go, 24. Let's try part B. From here, we need to isolate that logarithm, which means that 2 has got to go. Let's subtract 2 on both sides, which leaves behind, that was supposed to be log base 5 of this 2x minus 1 is going to be equal to, I've subtracted 2, so this is now 2. Okay, so now it is time to write this in exponential form. Exponential form, this base stays the same, so I'm going to bring you down and say, still have 5, and then I'm going to switch these two. I'm going to say, okay, it's 5 to the power of 2 now, and that's going to be equal to, and then this 2x plus 1 comes to the right side, and I say this is 2x minus 1. That actually does go faster than my method. I'm going to use his method from now on. That's so much nicer. All right, and then from here, I'm going to say, okay, 5 squared. I know who you are. You are 25. So I'm going to add 1 to, I'm trying to solve for x, right? I'm still going to add 1, so I'm going to say this is going to be 26 now is equal to 2x, and then finally, if I divide both sides by 2, I get x is equal to 13. Nice. Let's try part C. All right, so there's the logarithm that I need to isolate, which means I need to undo divide by 5. To undo divide by 5, I multiply both sides by 5. If I multiply by 5, multiply by 5, these 5s will cross cancel, leaving behind natural log of 2 minus x. And then on the right side, we now have a 5. Okay, let's do our change of form. So this is in the logarithmic form, and I don't see a base down here. So the question is, what is that base? The base is actually e. So I'm going to rewrite my base and say it's e to the power of, okay, I'm going to switch these two, right? So the 5 comes over here, and this is going to be e to the power of 5. And it's going to be equal to, this 2 minus x comes to this side, and I have a 2 minus x. All right, and I just need to solve now. So 2 minus x, let's go ahead and I'm going to do this clever thing where I'm going to add x to both sides because I like having a positive x. This is the, I don't know, you might not like that, but I prefer having x plus e to the power of 5. That's going to be equal to 2. And then from here, I'm going to get rid of this plus e to the power of 5 by subtracting an e to the power of 5. And I'm going to get x is equal to 2 minus e to the power of 5. There was another path that I could have done. I could have subtracted a 2 here to get over here and then multiplied the negative 2 plus e to the power of 5 by a negative 1. And then that would distribute in, giving a positive 2 and a negative e to the power of 5. That also would have worked. I like my way because I don't have to worry about multiplying by negatives. Those always scare me. So I don't need to box x though, I can just box the answer. So there's x. Weird rectangle, let's try you again. There we go. 2 minus e to the power of 5. All right, moving on to, oh my goodness. This is the hard bit because we have to worry about extraneous solutions. All right, so in general, we're going to get these two forms. We're going to get a logarithm is equal to a number, or a logarithm is equal to another logarithm. These bases should always match up. If they don't, there's a way to do it, but you probably have to do change a base, and it gets disgusting. It should be the same base. And I think that this one is easier because if this is all the same and this is all the same, then these two also have to be the same, so you can just set x is equal to y. You can essentially go like this and go like that, and x is equal to y, right? And then over here, you do what we've been doing up here, where you do the change of base form and then solve. So this is the key thing, though. We have to check for these extraneous solutions because what will happen is you'll get, the answer's -7. And you're like, okay, all of our answers has to be greater than 0. And you're like, oh no, we got -7. Sad face, the answer is no solutions. So you have to be wary. And that's usually the first thing that I check is what is the domain to make sure that I get the right answers. And this is kind of a funny note from Bryan Passwater. He says that it's just because you have log of x plus log of y and is equal to log of z, you can't just do this. And yeah, duh. Okay, you guys know, if you are adding the outsides, you're multiplying the inside. So the reason that this is wrong, you can circle this in your notes as well. You can't have a plus sign there. This is the wrong thing. If you can immediately jump to saying, okay, that's a plus and turn it into a multiplication, that's okay to do. That is valid. Just be careful. I'm going to be very careful in my notes to only use properties of logarithms so you can see why there's not a plus here and there's a multiplication symbol here, but that's usually the common mistake that most students will make. So we're going to check for extraneous solutions when we're doing these problems. So the way that I do that is I think, what are the bad things that can happen for my log function? Over here, nothing bad can happen. Over here, bad things can happen. I can never have the natural log of a negative. So where's the boundary point where this is a negative? And what I'm doing in my head, I'm saying, okay, x plus 4, I'm setting that equal to 0 because this is the boundary point where I become bad. If I'm at -1, then it doesn't work, right? So if I just solve this really quickly, x, and technically this is an inequality, right? Technically that's not equal to. I would say that x plus 4, this inside has to be bigger than 0. That inside has to be bigger than 0, which means x has to be bigger than -4. So this is the first restriction on my domain. And then here's the second. I also need to make sure that this inside of the logarithm has to be bigger than 0. This 5x minus 2 has to be bigger than 0. I don't know why I wrote that so low. We'll come up here and say the inside has to be bigger than 0. If I add 2 to both sides, I get 5x has to be greater than 2, and therefore x has to be greater than 2/5. So between these two restrictions, this is the most restrictive. Like if I get a number like 0, yay, it works for this one, but it doesn't work for this one. This one is really restrictive. So really what I'm saying is that's the domain. The domain here is, I'm going to circle this, not box it. This is really important. You need to make sure that whatever answer you get, it's bigger than 2/5. And this first one, it doesn't really matter too much because it does fall within 2/5. But in, I think, where's the first problem? In part C down, in part C down here, whoa, where are we? In part C down here, you'll see, okay, the domain restrictions are truly important. In part A and part B, we're just getting used to that form of how do we set up domain restrictions. All right, so let's solve this thing then. I want one logarithm on the left, one logarithm on the right. I have to use log properties to combine these two. Remember, if I'm adding the outsides, I'm multiplying the insides. So really what I have here is I have a log with base 10 because there's no base written, and I'm going to multiply 3 and x plus 4. I'm going to say log of 3 times x plus 4, and then on the right side, I'm just going to rewrite all of that stuff. I'm going to say log of 5x minus 2. So far, so good. And here's the key thing that is said up here. You have a logarithm equal to another logarithm if they have the same base, which I do in my problem. You just say, okay, the insides have to also therefore be the same. Look at this. One logarithm equals one logarithm. They have the same base. They have the same base. Therefore, the inside here is equal to the inside here. So I can come down here, and I don't want to skip. I will skip. I'm going to say 3 is going to be distributed in here. So I really have a 6, where did the 6 come from? That's not there. It's 3x plus 12. That's the inside. This and this match. And then that's equal to the inside over here, which is equal to 5x minus 2. So if the outsides match, then the insides have to match in order for this to be equal to, right? So I'll set the insides equal to each other, and let's solve. Let's move this 3x over. I'm going to subtract 3x on both sides. I'll show my work a little bit more on this one because I'm going to do two things at the same time. I'm going to subtract 3x, and if the x's are moved over here, that means this number has to be moved over here. So I'm going to add 2 and add 2. So you're gone, and I'm left with 14 is equal to 2x, and then from there, you divide both sides by 2, and x is equal to 7. And then this is the final check, right? Is our answer in the domain? Is 7 bigger than 0.4 or 2/5? The answer is yes. So this is a valid answer. Like I would say a good half the time on some of the harder problems, this answer is not in the domain. You have to check the domain. So we did get the right answer. We can go ahead and box the 7. Is that going to make a rectangle for me? It tried. It would help if I could write rectangles or draw rectangles. Okay, let's try part B. Again, we want to first find domain restrictions. So on this one, the inside has to be greater than 0. The inside has to be greater than 0. The inside has to be greater than 0, and it is. It's 7. Okay, so then I'm going to solve each of these. I'm going to say x has to be greater than -1. 3x has to be greater than positive 5. Therefore, x has to be greater than 5 divided by 3 is 5 divided by 3. So which of these is more restrictive? Well, plug in a number in between these numbers, right? Plug in 0. Is 0 bigger than -1? Yes. Is 0 bigger than 5/3? No. This one is restricting even more so, therefore that's the most restrictive domain, and I'll make a note to myself, here's the domain I need to check. Technically, I'm checking both the domains when I'm doing my answer, but I really only need to check the most restrictive domain, which is this one. Okay, so once we get our final answer, we will make sure it's bigger than, what is that, 1.666 repeating, or 5/3. So now let's actually do the problem. So the problem is I have two logarithms. I'm going to combine that into one logarithm. There's no coefficients out front that I have to worry about. I'm just using properties of logarithms, and I'm saying this number divided by this number because I'm subtracting the outsides, which means I'm dividing the insides. Over here, I'm going to say this x plus 1 is being divided by 3x minus 5, and that's going to be set equal to the other side. Sorry, that's I need to take my time. That is the inside of, come on now, that's the inside of my natural logarithm. And then on the other side, I have natural logarithm of 7. Okay, so I've done my properties of logarithms, and now I'm saying, hey, outsides, this is base E, so the outsides here match, therefore the insides also have to match, and therefore I can say the next step is x plus 1 over 3x minus 5 is just equal to 7. Okay, so I've gotten rid of logarithms. I just changed this into a rational equation. The way that we deal with rational equations is you cross multiply. You say, okay, the fancy way of saying this is I multiply both sides. I don't have to write this. 3x minus 5. I multiply that side by 3x minus 5. I multiply this side by 3x minus 5. But really what you're doing here is you're just moving the diagonal up here. Move the diagonal up here because what you're essentially doing is you're gone. I essentially have x plus 1 is equal to, here we go, distribute, and I get 21x minus 35. That was the equivalent of just bringing the 3x minus 5 up here, and it's no longer down there because I moved it up here. If you prefer doing it this old-fashioned way, that also works. Okay, we just need to solve for x here. So to solve for x, what do we need to do? We need to, let's move the x's to the right side. So I'm going to subtract x, which means this number needs to move over here. I'm going to add 35, gone, and I'm left with 36 over here and 20x over here. Dividing both sides by 20 reveals x is equal to 36 divided by 20, which reduces, I think they both have a 4 that can pop out of them, right? That's going to be 9 and 5, I think. So this is equal to, let's do a different color. This is equal to 9 over 5. So there's my answer. I think the answer is 9/5. Is that correct? Well, check the domain. Come on, really? Check the domain. Is 9/5, which is about, it's almost 2, is, oh, you have to be really careful here. This as a decimal, here, let me help us out. This as a decimal is exactly 5/5 plus 4/5, or 1.8. And this as a decimal is 3, come on now. This is, why did I say approximately equal to? It is exactly equal to. Come on, Mr. Sindel. You know the difference between approximately and equal to. This is equal to, and that was equal to. So this is equal to 3/3 plus 2/3, which is 1.6 repeating. So is 1.8 bigger than 1.6 repeating? Am I in the domain? Yes, this number is bigger than 1.6 repeating, so it gets the check mark. That is the correct answer. You always, at the very end of these problems, unfortunately, when you have multiple logarithms, you have to check that you're in the domain. And that kind of brings up a point of, why weren't we checking the domain up here? Well, we only had one logarithm, and you can't really change the domain with one logarithm. When you have multiple logarithms, now we've got to check the domain. We have multiple logarithms, right? So over here, multiple logarithms, got to check the domain. Got to make sure the inside is greater than 0. And I did promise that this one, you'll actually have to exclude at least one answer. So you have to make sure that the inside, this inside, has to be greater than 0. You have to make sure that the inside has to be greater than 0. Solve each of these. X has to be greater than -2. X has to be greater, that's equal to, X has to be greater than 3. This is the more restrictive domain. So we're going to say the domain restriction is X has to be greater than 3. That's the one I'll check at the very end. From here, we're time to solve this, right? We're going to say a logarithm and another logarithm. If I add the outsides, I'm multiplying the insides. So I really have, on the inside, I have x plus 2 times x minus 3. And that's on the inside. What's on the outside is a log base 3 of all of that stuff is equal to a log base 3 of, what's the right side? 14. All right, and then from there, I'm going to go ahead and say, hey, look, the outsides are exactly the same, therefore the insides have to be the same, and I can say now, let's go ahead and multiply these together because that's the only way to move forward with this problem. I'm going to say x times x is x squared. Let's do this in a different color. X squared. X times negative 3 is negative 3x. 2 times x is a plus 2x. 2 times negative 3 is a negative 6. That has to be equal to a 14. Simplifying, and I want this right side to be equal to 0 because I'm going to have to do some more ninja starring or some more factoring. I'm going to say on the right side is going to be equal to 0. Let's do this in a different color though. Right side is going to be equal to 0. The left side, simplify x squared. Okay, these two terms combine, so negative 3x plus 2x is just a negative x. And now what I'm really doing here is I'm subtracting a 14 and subtracting a 14. So these two turn into a negative 20. And then from here, I'm going to try to factor this. So this is asking the question, what two terms multiply to negative 20 and add to negative 1? That's this question here, right? And the answers are negative 5 and positive 4. So what I have down here is an x minus 5 and an x plus 4 is equal to 0. And then from here, you can use the zero product property and say this could be equal to 0 or this could be equal to 0. You can say that, running out of colors here, you'd say x minus 5 is equal to 0, or this x plus 4 could be equal to 0. Solving each of these gives you x is equal to 5 and x is equal to negative 4. Okay, these are the final two answers, right? They're not final. So they're not final because we need to check them against the domain. 5, is 5 greater than 3? Yes. Negative 4, is negative 4 greater than 3? No, negative 4 is not even greater than negative 2. Negative 4 is outside the domain. Therefore, we're going to say this one, not in domain. And therefore, the answer is just 5. We'll box the 5. And moving on to part D, we have, again, 2 logarithm. But notice this, there's only one that has an x in it, so we don't actually need to check the domain in this one. X has to be greater than 0, but I don't think that's a possibility of changing the domain. So I'm not going to worry about it in this one. On this one, I have 2 logarithms. I'm using properties of logarithms. I'm going to say that I going to still have natural log. If I'm subtracting the outsides, I'm dividing the inside. So I have x divided by 3 on the inside, and that's going to be equal to 2. Okay, this is one of those scenarios where I don't have a logarithm equal to a logarithm. From here, I'm going to do the change of form. I have logarithmic form. Let's change this to exponential form. This hidden base down here was base e. So I really have e to the power of, and I'm going to switch these two, right? So I'm going to say 2 comes down over here, e to the power of 2, and this x to the power of 3 comes over here to the right. I'm going to say this is equal to x over 3. This is now exponential form. And then from here, I need to solve for x, so I need to multiply both sides by 3, multiply by 3, multiply by 3, and my final answer is x is equal to 3e squared. I guess we could check against the domain. X has to be greater than 0. This is a positive number, therefore it is bigger than 0. We didn't really need to check the domain, but I just did a sanity check right there. 3e squared. Nice. Okay, so that was page 2 of 3, and then we get to the very, very difficult page 3 of 3. I'm imagining if there's students that are trying this on their own without watching the video, this is where you're going to watch the video. It's really hard. Okay, here we go. Example 4. So we've got a bunch of logarithms happening. The problem here is we need to check the domain first, and then you have a 3 out front. This means that the 3 is going to have to come up to the power eventually, but first, check the domain. What do we have? We have to have the inside be bigger than 0. That inside is already bigger than 0, and this inside also has to be bigger than 0. This x plus 7 has to be greater than 0, and if I subtract 7, x has to be greater than negative 7. This is the more restricting of the 2 domains, so this is the one that I'm going to check for domain. In pen. Check the domain that x is greater than 0 at the very end, Mr. Sindel. So now I'm going to use properties of logarithms. Just remember that this 3 is going to come up here, so it's really 2 to the power of 3. And if I subtract the outsides, I'm dividing the insides. So I'm going to do that right now. I'm dividing the insides of x is being divided by 2 to the power of 3. That's still all in a logarithm. Log base 4 of all of that is equal to log base 4 of all of this x plus 7. And hey, outsides are the same, therefore the insides have to be the same. And I'm going to say now a new equation without the logarithms is x over 8, you should know your cubes, is equal to x plus 7, and I can solve. Let's go ahead and I don't like fractions, so let's go ahead and multiply this side by 8, and multiply this side by 8. Remember, that's being distributed into each of these two terms, so if I go yoink, yoink, I get the following. I get just x because the 8's cross cancel, and then on the right side I get 8x plus 56. And I need to move the 8x on over, so if I do that I get negative 7x is equal to 56, and then divide both sides by negative 7, and you get x is... Oh, 56 is not divisible by 7. That's rough. Okay, x is equal to, that's a weird equal to, x is equal to a negative 56 over 7. No, 56 is divisible by 7, isn't it? 7 times 8 is 56. My mind is weirdly blanking. Okay, that's equal to negative 8. Sorry about that. It is equal to negative 8. And okay, so we're done, right? The problem here is the domain has to be greater than 0, but we got negative 8. So because, and I'll write the note here, this one is not in our domain, that means the answer is no solutions. All right, let's try another, shall we? Again, check the domain. So this inside has to be greater than 0. This inside has to be greater than 0. It is, so I don't need to write it. And this inside needs to be greater than 0, so I need to say 2x minus 7 needs to be greater than 0. This one needs some solving. Let's add 7. 2x needs to be greater than 7. And then let's divide by 2, and x has to be greater than 7 halves, which is the same thing as 3.5. So x needs to be greater than 3.5. That's the domain that I want to check. That's the most restrictive domain. That's the bigger of the two numbers, the more positive of the two numbers. All right, use properties of logarithms. This one is kind of the same thing where 3 is going to come up here. And if I'm adding the outsides, I'm multiplying the insides. So if I'm multiplying x times 2 to the power of 3, that's the inside, and I have log base 10, because we don't see a base, so you assume the base is 10, is equal to log base 10 again of this 2x minus 7. Okay, these insides are different. Okay, the outsides are the same, therefore we set the insides equal to one another, just like in the last problem, and we say 8x is equal to 2x minus 7. And then we're going to subtract the 2x on both sides and get 6x is equal to negative 7. Divide both sides by 6, and x is equal to a negative 7, 6, which is equal to negative 6 over 6 minus a 1 over 6, which is equal to a negative 1.16-ish. Isn't it like a half a third? So is it like 0.155? I have a calculator up on my computer. I can just do 1 divided by 6-ish. It's 0.16, not 1.5. Negative 1.16. Okay, so check this out. Is our answer, is negative 1-ish bigger than 3.5? The answer is no. This one is, again, not in the domain. Therefore, the answer, yet again, is no solutions. All right, we're moving on to example 5. So, okay, these guys are rough. Okay, we need to find where graphs of f and g intersect, which means this thing is going to be set equal to this thing. That's what it means. When you say intersect, that just means set the two functions equal to each other. So we do that. We're going to say natural log of x plus 10 minus natural log of x. We're going to set that function equal to the other function, which is just, what is it? Come on, fingers, scroll over. We have natural log of x plus 3. X plus 3. All right, so we set them equal to each other, and then it's the same problem yet again. So let's check the domain restrictions. So this one, the inside has to be greater than 0. the inside has to be greater than 0, the inside has to be greater than 0. So if I do some solving, this one is, x has to be greater than -10. That one's still x is equal to 0. This one is x is greater than -3. The most restrictive of all of these is actually this one. The domain has to be greater than 0, because that's the more positive of the three numbers, and now I can solve. So using properties of logarithms, I can say that if I'm subtracting the outsides, I am dividing the insides, and I have x plus 10 dividing x. That's technically inside of a natural logarithm, and that's going to be equal to the natural logarithm of x plus 3. I really should have changed the color there. It's kind of annoying that it all matches. So let's go ahead and change the color of you to like a blue. And then if the outsides are the same, then the insides have to be the same in order for this equal sign to be true. So I have x plus 10 all over x should be equal to an x plus 3. I'm also realizing I'm wasting some room, which is a little bit annoying. So stop wasting room, Mr. Sindel. And then from here, let's go ahead and I have to get rid of that x. I don't like fractions, so I'm going to multiply this side by x, multiply this side by x, so that these two x's cross cancel, leaving behind an x plus 10 is equal to, again, we have to distribute this x into this entire side, so I'm left with an x squared plus 3x. Let's just move everything to the x squared side, because this x squared needs to stay positive, so I'm going to subtract an x and subtract a 10. And that's going to give me 0 is equal to x squared. I am subtracting x, so plus 2x. Subtracting the 10 is subtracting the 10. And then from here, I'm thinking of a ninja star, right? Thinking of a ninja star, things that multiply to -10 and add to positive 2. We have 1 and 10. That doesn't work. We have 2 and 5. That would be 3. Oh no, ninja star does not work. Therefore, it's a quadratic formula. All right, here we go. If you have forgotten the quadratic formula, it is this. Where do I have? I guess I'm choosing blue. We're going, yeah, blue. X is equal to -b plus or minus square root b squared minus 4ac all over 2a. All right, so I have quadratic formula set up. Remember that a here is equal to 1, b here is equal to 2, and c here is equal to -10, and I'm just plugging into our formula. So our formula goes like this: x is equal to -2 plus or minus square root b squared is going to be 2 squared minus 4 times a is 1, and c is -10, all over 2, what's a is 1, 2 times 1. Oh my goodness. What do we have from here? Okay, I am going to simplify this on the right-hand side. Okay, this could be -2 plus or minus, okay, inside here is going to be 4, okay, a negative times a positive times a negative is a positive, so I'll put a plus sign here. And then 4 times 10 is 40, times 1 is meaningless, it's still 40. And that's all over 2. I guess I didn't have to have such a long square root, did I? Square root of 44 is, here, give me a sec here. It's going to be equal to -2 plus or minus root 44 over 2. But I think root 44 can be simplified. Let me do some scratch work where I have room. Root 44, if you didn't know, is the same thing as root 4 times root 11. And root 4 is the same thing as 2. So it's really equal to 2 root 11. That might help simplify some things. This is going to be equal to -2 plus or minus 2 root 11 all over 2. Notice that each of these has a 2, so this, and this are all going to simplify. And this is going to turn into a -1 plus or minus 1 root 11, which is just root 11, all over 1, which is just -1 plus or minus root 11. All right, so there are two different answers here, right? So one of the two answers is -1 plus root 11. The other answer, hold on, get the arrow there. The other answer is -1 minus root 11. those are the answers. Okay, are they in the domain? I don't know. Where's the domain? Domain has to be greater than 0. So, which of these numbers is greater than 0? Well, this one is clearly negative and then even more negative. The square root of 11 is bigger than the square root of 9. So this one, I can say this one is greater than square root of 9, which is therefore greater than 3. So if I have a number that's greater than 3 and I subtract 1, this one is in the domain. This one is not in the domain. So I'll make a note here. This one is not in our domain. Therefore, the answer is just -1 plus square root of 11. Whew. All right. That was rough. I'm not going to lie to you. Okay. Let's do example 6. In the xy plane, what are all the x-coordinates points of intersection? So points of intersection, again, you're setting one function, this entire function, equal to the other function. So, setting these things equal to each other, let's go ahead and do this. We have log base 3 of 2x minus 3 plus log base 3 of x plus 4. That's going to be equal to the other function, which is log base 3 of 8x plus 2. Log base 3 of 8x plus 2. I wrote everything correctly. I don't want to make a mistake in just copying things down. Okay, these two are being set equal to each other. So using the properties of logarithms, if I'm adding the outsides, I'm multiplying the insides. And the insides are really going to be 2x minus 3 times this x plus 4. Okay, technically all of that is inside a log base 3, and therefore the right side is also a log base 3 of still of that 8x plus 2 haven't changed. Okay, check this out. Outsides are exactly the same, therefore the insides have to be exactly the same. I'm going to come back down here and I'm going to say this is now, okay, I'm going to multiply. 2x times x is 2x squared. 2x times 4 is an 8x. And negative 3 times x is a negative 3x. And negative 3 times positive 4 is a negative 12. That's the left side. The right side is still 8x plus 2. All right, we need to simplify. I like putting everything on the side where the x squareds are positive. So we're going to say we have a positive 2x squared over here. Okay, let's do some simplification. If I have an 8x on this side and 8x on this side, these two cancel out because I'm subtracting 8x. I'm subtracting 8x, and I'm left over with a negative 3x. And then I'm going to move the 2 one over, so I'm technically subtracting 2, which means I have a negative 14, and that's equal to 0. All right, so from here, I'm going to do another ninja star to factor. So this one is an advanced ninja star. I'm going to do that work over here. So the way that I do my advanced ninja stars is I say, okay, these two numbers, multiply them. I get negative 28. That was a negative 8. Negative 28. I'm writing 2x here and 2x here, and then the number that they add to, negative 3, down here. The ninja star is now set up, and I'm going to knock down the ninja star. I'm going to say, okay, what two numbers multiply to negative 28? They're still multiplying to negative 28 and adding to negative 3. So factors of 28. 1 and 28, not helpful. 2 and 14, not helpful. 3 doesn't go into it. 4 and 7. Ooh, 4 and 7 can get to it. 3. So I'm going to write down 4 and 7. I'll figure out the negative one in a sec. So bigger is negative, bigger is negative, and I think I have my ninja star set up. Okay, so I'm going to simplify each of these fractions of my ninja star. This one is going to turn into 1x over 2 if I divide the top and bottom by 2, and this one's going to stay 2x over negative 7, which means my ninja star is done, and I have x plus 2 times this 2x minus 7. 2x minus 7 is set equal to 0, and then we're using the zero product property, and we're going to set each of these pieces equal to 0, so x plus 2 is equal to 0, and this 2x minus 7 is set equal to 0. Subtracting 2 gives us x is equal to negative 2. Adding 7 gives us 2x is equal to 7. Dividing by 2 gives us x is equal to 7 halves, which is 3.5. Okay, so those are the answers, but which of these answers are in the domain? 3.5 and negative 2. I said that the domain is God darn it, I forgot to do the domain. I knew I was missing some red. Okay, so very tiny. Here, I can scooch these guys up a little bit. I can say move you up to right there. Move these guys up to right there. Move these up to right there. I'll do the domain down here. So I have to say the inside, whoa, 2x, and it's okay to do the domain at the very end. 2x minus 3, the inside has to be greater than 0, therefore 2x has to be greater than positive 3, therefore x has to be greater than, x has to be greater than 3 halves, or 1.5. The inside has to be greater than 0, therefore the inside has to be greater than negative 4, and the inside has to be greater than 0, therefore 8x has to be greater than negative 2, therefore x has to be greater than negative 2/8, which is the same thing as negative 1/4, which is the same thing as negative 0.25. Okay, which of these is the most positive? U. So U are the domain. So we're going to say domain is right there, be greater than 1.5. So is this number greater than negative, or is this number greater than 1.5? No, this one is not in the domain. I'll point to this. And 2.5, this number is bigger than 2.5, therefore that is the final answer. And you can leave it as a fraction. You can say 7 halves. Whew, all right, and then we're on to our final example. If you have multiple exponential functions, then it's pretty straightforward. You just set the exponents equal to each other as long as you have the same base. So I'll show you what I mean. In example 7a, we have the same base. If the outsides are the same, then these insides, I'm trying to use the same terminology. If the bases are the same, then the exponents have to be the same in order for us to put this equal to sign. Therefore, this and this are equal to each other, and we say 5x minus 1 has to be equal to this 2x plus 7. From here, we're just going to solve. We're going to, here, let me be very specific. Minus 2x, and at the same time, if these are gone, then I also have to do plus 1, so those two are gone, leaving behind a 3x, which is equal to an 8, and then divide by 3, and x is equal to 8/3. The cool thing about these problems, there's no logarithms, there's no domain restrictions, we're just done. It's 8/3. Nice. All right. What about part B? Okay, these bases are not the same. So how do you make them the same bases? My strategy is make them as small as possible. 2, you're already as small as possible. 8, you can get smaller. Okay, let me go ahead and write the power of 3x minus 2. What thing comes down here? How do I make this 8 smaller? And the answer is, well, that's really 2 to the power of 3. And then over here, I'm not going to change anything. It's still 2 to the power of x plus 5. Did you know if you have a power to a power, you multiply those powers, which means I really have a 2 to the power of, if I distribute here, 3 times 3x is a 9x, and 3 times negative 2 is a negative 6, is equal to this 2 to the power of x plus 5. And hey, check this out. Same base, therefore these powers also have to be the same. And I'm going to run out of room, so let's go ahead and do this over here. And I'm going to say, okay, that means that 9x minus 6 has to be equal to x plus 5. And then from here, we're going to subtract x. We're going to, now I'll cancel out that one. Therefore, I have to add 6, canceling out u, add 6. And what is left over? We have an 8x, which is equal to 11. And then finally divide both sides by 8, and x is equal to 11/8. And again, no domain restrictions, so we're just done. It's just 11/8. All right, moving on to part C. Again, we have to have the same base here. Unfortunately, we can't do 9 to any power to get 27, but hey, this one can get even smaller as well. So here, let me go ahead and rewrite the powers. The powers are something to the power of 2x is equal to something to the power of x plus 2. I'm just going to rewrite 9 as 3 to the power of 2. And guess what 27 is? You have your perfect cubes memorized, so you know that's 3 to the power of 3. And again, a power to a power, these two are powers to a power, you multiply them, and this is really 3 to the power of 4x. 3 to the power of 4x. And over here, this is 3 to the power of, again, you're going to multiply. 3 times x is 3x, and 3 times 2 is 6. And check it out. If I have the same base, these exponents have to be the same for this equal to sign to actually exist. So I'm going to say, hey, the exponent 4x has to be the same as the exponent of 3x plus 6. subtract 3x, and you get x is equal to 6. Final answer, box. And the last problem of notes, only part 1. We still have part 2 to go. Part 1. Here we go. Oh, this one is tricky. Okay, so again, I'm going to start the same way. It's like something to the power of 5x plus 7 is going to be equal to something to the power of x. Make them as small as possible. Well, that one's easy, and this one can turn into a 2 to the power of 2. 2 to the power of 2. But this one, okay, it has to be the same base, so I must have a 2 in the bottom. 2 to what power is 1/2? And you might remember, oh yeah, that's right, to flip something, I have to have a negative power. 2 to the negative 1, this is a power of 1, flipped up here and became a negative, right? So therefore, I have that. And then what do? We have, oh yeah, we can say, okay, negative 1 is going to distribute into both of these. I'm going to say this is 2 to the power of negative 5x minus 7 is equal to 2 to the power of, multiply 2 times x is 2x. And then you set the exponents equal to each other. You're going to say, oh yes, this negative 5x minus 7 is the same thing as 2x. Let's go ahead and bring the 5x over. We're going to say now negative 7 is equal to 7x. Dividing both sides by 7 gives us x is equal to negative 1. And we get our final answer, box it, no domain restrictions. It's nice, it's not a log problem. And we are done with notes part 1 for topic 2.13 on AP Precalculus's exponential and logarithmic equations and inequalities notes. Oh my God. Okay, so there's the third page, there's the second page, there's the first page. I will see you for notes part 2.